back up for a second. And now I'm going to take this notion, all right, that our atoms are unique. They're based on the number of protons. Add a different number of protons, and you have a different atom. Add a different number of neutrons, and you have a different flavor of that same atom. Okay? So if we want to know now how many atoms we have, remember, these things are tiny. They're so tiny. We're never going to be able to mass them individually. But we can mass them with a collection. Okay? Or vice versa, if we want to know how many that we have, how many atoms we have, we can count them by weighing. Okay? So for example, suppose we go to the fair. Oh, and I was so looking forward to the Humboldt County Fair this year. Damn Rona. Okay. Anyways, so you go to that little game, right, where the guy's like, how many jelly beans do I have in this jar? And you try to guess, and if you guess right, you get all the jelly beans. Okay? So obviously, you all are intelligent enough people to know it would be impossible to count all of these jelly beans. And imagine now just for a second, they're not jelly beans, but they're atoms. It would be especially impossible to do that. Okay? But suppose we get our hand on one of them, maybe 10 of them even, and we weigh them. We take an average, right? Look, here's our average. One mass was 5.1, 5.2. Oops, I should have said 5.0, right? So we have the same level of precision for each measurement, okay? And we get an average that is 5.0. So then when the guy's not looking, we weigh the entire jar, and not including the mass of the jar itself, right? But we say that the jar is 5.54 kilograms. So that's now 5.45 kilograms. Oops, wait a second. Let me, yeah, we can do it like this. Okay. So we could say in 1 kilogram, we know there's 1,000 grams, right? So then now I can then finally also say, well, I know that 5.0 grams is 1 jelly bean. So remember, I went down, up, down, up, down, up. Okay? 5.45 kilograms. In 1 kilogram, there's 1,000 grams. 5 grams is 1 jelly bean, so all of those cancel. And what I'm left with is how many beans that I have. And if I were to go and do this number, I would get 1,090. Okay? So this is exactly how we take the mass of atoms, exactly how we count atoms. We recognize that some atoms, for example, sodium, some are going to be sodium 23. Some of them are going to be sodium 24. And so when I go and scoop up a pile of sodium, some's going to be 23, some's going to be 24. So the amount of sodium I have is going to be some average. It's going to be some average mass. Just like when I scooped up these jelly beans, some were 5.1, some were 5.2, some were 4.8, etc. But I was still able to count pretty well by taking the average. That's what we have with atoms. Okay? So let's talk about the mass spectrometer. So the mass spectrometer is an amazing device. As you can see, it looks pretty similar to J.J. Thomson's cathode ray tube. It got inspiration from J.J. Thomson's cathode ray tube. And the way this device works, you put a sample, and I'll just write atoms or molecules. That's what our sample is. We throw them into this device. This heater vaporizes them, so it turns it into a gas. Okay. We have this electron beam, and that electron beam is going to be very similar to the X-ray beam in Robert Millikan's device. So it ionizes these atoms or molecules. Okay. And you have, again, more electrically charged plates that will accelerate those ions, okay? And then, of course, they enter this magnetic field, and what happens is the least massive ions are able to bend more than the most massive ions. So again, if we have this collection of atoms and molecules, we scoop up our collection of atoms and molecules. Some of them will be one flavor Another will be a different flavor, right? Some will be heavy, some will be light. The mass spectrometer can actually separate those by their mass, and not only separate them by the mass, but calculate what the mass had to be. So imagine if we took a sample of neon. So neon is a noble gas, makes pretty colorful lights, like a neon light, duh, okay? So if you throw some neon into this mass spectrometer, the mass spectrometer would actually tell you there's 3 flavors of neon. You would never guess with your naked eye, but there's 3 flavors of neon. Neon 20, neon 21, and neon 22, okay? Obviously, neon 21 has 1 more neutron than neon 20, and neon 22 has 2 more neutrons than neon 20, all right? And so what the mass spectrometer is able to determine is the exact mass. And I want to stress the exact mass in atomic mass units, AMU. We're going to get into that soon. I think probably the next lecture, the atomic mass unit. Anyways, for now, just think of this as a number, okay? And so you can see neon 20 is very close to 20. It's 19.992, but all the same, it's very close to 20. Neon 21 is 20.994, very close to being 21. And neon 22 is 21.991, being very close to 22, okay? So these are the exact masses. The average mass of neon is a result of all 3 of these. So when I go and scoop up some neon, it's impossible for me to separate those different isotopes. So the amount of neon I have would be based on some average. It would be like this number right here. Even though I know some of them I've scooped up are 20, 21, or 22, just like the jelly beans. Some of them I've scooped up are 5.2, 4.8, etc. Okay? And so what this mass spectrometer can tell us is how abundant each of these isotopes are. And so it would determine that neon 20 is by far the most abundant based on the size of this peak. So in other words, this detector plate right here would be getting hit by neon 20s on average more than neon 21 or 22. So you can think of this as like counts, this peak, like how many times that particular mass has hit the detector, okay? And so that's what we call the natural abundance. So neon 20 is 90.6 natural abundance, all right? You don't have to memorize these numbers because we can find them on the periodic table. So this is the last little bit that I'm going to talk about, okay? And then I'll end this lecture because I think this has been going on for a little bit, all right? So let's talk about average and exact masses. So we've talked about exact masses, right? That's what this whole thing is about. So what's the average mass, okay? Well, the average mass is the average of all of the exact masses. Okay, not too bad, okay? And as it turns out, okay, our atomic masses, the AMU, are entirely based off of carbon-12, carbon flavor 12. I don't know if you knew that or not, but we've based the entire periodic table of masses off of carbon flavor 12, okay? So we have to set the scale somewhere, right? So we say carbon-12 is exactly 12 AMU. We also call this Daltons for the name of the scientist, John Dalton, okay? So you can say 12 12 Daltons, and that equals 12 AMU, okay? So as it turns out, in the original, setting up of all these masses and the original, programming of the first mass spectrometers, you had to give it some type of known mass. So that's called calibrating. So we had to calibrate the mass spectrometers somehow. So all mass spectrometers in the periodic table has been calibrated off of carbon-12, okay? And so now what you're able to do based on how much the light particle separates from the heavy particle, and if you're having a hard time understanding this analogy, just imagine you're driving in a race car and you're going around some turn and you're in some super light car, like maybe a Honda Civic, and somebody else is in like a massive truck, and you're both going the same speed. Just imagine like both people throwing the wheel and how easy it would be for the Honda Civic to make that sharp turn versus like the big massive truck, okay? And doing a lot of physics and calculus and math, you can then say, well, what had to be the mass difference between those based on that deflection, okay? So for example, if you wanted to know, well, how much does a carbon-13 weigh? So what the mass spectrometer actually does is take the ratio. Okay, so now if I say the mass of a carbon-13 divided by the mass of carbon-12 turns out to be 1.0836129, and the precision is just being on and on and on and on and on and on and on. Okay, always updated to have more and more and more precision. So that means through algebra, because we know the mass of carbon-12 has to be exactly 12, so if this is exactly 12, and I mean like no sig figs, like exactly 12, then we can do algebra, right? Multiply both sides by 12, and then you separate carbon-13, and thus the mass of carbon-13 has to be 13.003355 AMU. That is the exact mass of carbon-13. The exact mass of carbon-12 is exactly 12. Okay, so then how do we get the average mass? Okay, one last slide.